Hey guys, Mr. B here, and in this video we're going to be going through Chapter 20, Section 1 notes on electric charge and static electricity. So let's begin here and just talk about what is electricity and what is electric charge. Now, there's a lot of vocab in this section, but we'll do the best that we can to kind of break it down, make sure we understand what they're talking about. All right, so what is the source of electric charge? All right, so remember that all matter around you is made out of atoms. And in atoms, there are three different types of particles, but two of them have electric charges on them. Okay, there are protons, which are positive charged, and there are electrons, which are negatively charged. Then there are also neutrons, but neutrons don't have a charge. So we don't typically talk about neutrons when it comes to charges. But remember that electric charge is a property that all matter has because all matter is made out of atoms and all atoms have protons and electrons inside of them. Okay, so the charge that a piece of matter will have is going to be dependent on how many protons and how many electrons it has. Now, typically, the number of protons and electrons are going to equal each other. Okay, so most matter does not have a charge on it because the total positive protons and the total negative electrons are always going to be the same. Therefore, they balance out and you get a charge of 0. However, it is possible for an atom to gain or lose electrons, in which case it will become positively or negatively charged overall. And once it has a charge, from that point then, it can interact with magnets, it can interact with electric circuits, and we start to get things that we call electricity. Okay? So, an excess or shortage of electrons is something that we call an electric charge, and it produces a net electric charge. Okay, so if you have more electrons than you usually would have, you're going to have a negative charge. If you have less electrons than you usually would have, you're going to have a positive charge. So this is where charges come from. Okay, every piece of matter around you can have an electric charge on it if you either somehow give it electrons or take electrons away from it. All right, so how do electric charges interact with each other? Now, we know that electric charges, of course, are all around us now, but how do they interact with each other, positive and negative? So we should know that electric charges interact by either attracting or repelling each other. And this is probably not new information to you. You do probably know that opposite charges attract and similar charges repel. But we're going to talk a little bit more about what actually is going on. Okay. So if you have two charges that are both positive or both negative, they will repel each other. Okay, so similar charges will repel each other. And this is a pretty important concept to remember. Okay, so similar charges repel. Oh, I forgot that it's going to go behind the picture. There we go. However, if we have opposite charges, so one charge is positive, the other charge is negative, they're going to attract each other. So similar charges repel and opposites attract. So this repulsion or attraction is what we call an electric force, kind of like a physical force, right? If you push on something with your hands, this type of force can be a push or a pull, but it's of course being caused by electric forces rather than physical, objects doing the pulling or pushing. So we call it an electric force. Now in this image, we see this girl who has a balloon, and I'm sure you've done this before, where you take a balloon, you can rub it on your shirt or on some, soft material. You hold it near your head, and your hair will get pulled to it, or actually you rub it on your hair, and it will attract your hair. That's because when you take the balloon and you rub it on your hair, you're actually stripping electrons off of your hair and depositing them on the outside of this balloon. So the balloon is overall going to have a negative charge on the outside. Likewise, then your hair is going to have a positive charge on it because you've taken electrons away from it. So it has a shortage of electrons, therefore it's now positive. And the balloon has an excess of electrons. It has more electrons than normal, therefore it's negative. So you have opposite charges and you get this attraction, right? And your hair will attract to the balloon. A very common thing that I'm sure most of you have done or seen before. All right, so this charge has an attraction or repulsion on other charges that are nearby. And we call this effect an electric field, okay, kind of like a magnetic field. So all charged particles are surrounded by electric fields. An electric field is essentially just the effect that that charge will have on other charges that are in the space around it. Now, whenever we draw electric fields, we draw lines that show what direction the forces would be pulling or pushing if this charge were interacting with another positive charge, okay? So on the left here, we have a positive charge, and it will have an electric field where we will draw field lines or arrows representing electric force pushing away from the charge. So if another positive charge were to come near this one, that positive charge will get pushed away. Okay, it would be repelled. Likewise, on the right here we have a negative electric charge, and we will draw electric field lines that are pointing inwards towards the negative charge. So if a positive charge were to come nearby this one, it would get pulled in, right? It would get attracted because opposite charges attract. So an electric field is just the effect that a charge will have on other charges nearby, whether it's going to repel that other charge or attract that other charge. We will draw lines that show what direction that force is going to be applied, okay? So the strength of any electric field is dependent on two things. One, it's dependent on how big the charge is that is creating the electric field. So if you have a very large electric charge, it will have a very big electric field around it, and therefore it will have a very big effect on other charges nearby. The other thing that can determine the strength of an electric field is how far away you are from the charge that's making the electric field. So if you're nearby this electric charge, you will feel much more impacted by its electric field, whereas if you're further away, that electric field is going to be a lot weaker, and you're probably not really going to feel its effects so much. Okay, it's kind of like a gravitational field, right? Earth has a gravitational field around it and gravity. If you're on the surface of planet Earth, its gravity will have a very big impact on you. Therefore, you're going to feel its gravity all the time. Also, the bigger a planet is, the stronger its gravity. So planet Earth, of course, has a decent amount of gravity, but compared to planets like Saturn or Jupiter, they have a much, 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 much stronger gravitational field than planet Earth does. So the strength of a gravitational field is dependent on how big the planet is, just like the strength of an electric field is how big the charge is. And also how close you are to the planet will have a bigger impact on how much gravity you feel. Same thing with an electric charge. The closer you are to the charge, the more impact you're going to feel from its electric field. All right. Last thing here to talk about is static electricity. No, not last thing, but second to last thing. Now, static electricity is something that you're probably all very familiar with. In the wintertime, especially here in Minnesota, when we go to touch doorknobs and metal objects, we will shock ourselves because the air gets very dry, and building up electric charge is a lot easier in the wintertime. But what exactly is static electricity? So static electricity, okay, the word static, this is an important word to understand. The word static means non-moving. Okay, if something is static, that means it's not changing, it's not going anywhere. So static electricity is essentially electricity that is sitting in one location and it's not going anywhere. So it builds up, okay? And when you build up this electric charge, whether it be positive or negative, it can then move somewhere if an opposite charge comes nearby. So in the wintertime, since it's very dry in the air, it's more difficult to get rid of electric charges off of our body. And you will accumulate electric charge through a multitude of ways, but the main way is through friction. So when you rub your hands on clothes or just objects in general, you will build up electrons on the surface of your skin. And over time, as more and more electrons get built up, you'll get a bigger and bigger deposit of electrons until, of course, you come nearby something that has a charge that is opposite from you, in which case the electrons on your hand are going to be attracted to that opposite charge, and they're going to jump. And when they do that, they will oftentimes jump through the air. So when you go to reach out for something, they'll jump through the air before you actually touch that object, and you will get a shock or a spark that will sometimes go through the air. Okay, so this is what we call static electricity. You have a buildup of charge, and when that charge comes nearby another charge of the opposite kind, it will want to jump to that charge, okay? And a lot of times you'll see a spark and you'll feel a shock, and we call this a static shock or a static discharge. Now, this is going to be different from electric current, which we'll learn about later in this chapter. But either way, okay, you have a buildup of charge. Now, the excess negative charge, again, can be discharged through a spark. The electrons will jump through the air, and they'll be negatively charged, and they'll jump to a positively charged object or a neutral object. And essentially, again, once they go there, then they'll travel through the object down into the ground, and then there they will disperse themselves into planet Earth, okay? All right. Now, when it comes to building up charge, there's 3 ways that we can build charge. Okay, and this is an important thing to know for this chapter. So I'd recommend writing these down or just really making sure that you pay attention for this one. So the 3 ways we can transfer charge. First one is induction. Okay, induction is when charge is transferred from a distance without direct contact. So a primary example of this is when you shock your hand on a doorknob. You have charge built up in your hand. You bring your hand near the door. The charge in your hand travels through the air, usually through a spark. It gets to the door, and then the door gets charged, but then the charges will disperse themselves through the door down to the floor. Okay, that's induction, where you're charging from your hand to another object. No direct contact. Then we have charging through friction. Friction, of course, is when you have 2 things rubbed together. So you can do this, of course, if you take a balloon and you rub it on your hair, you will strip electrons off of your hair, deposit them onto the balloon, and you now have a charged balloon. Okay, you've stripped or moved charges through friction. And the last that we have is conduction. Conduction is transfer by direct contact. So if you were to charge an object and then touch that object to something else, the charges can transfer their way from the first object to the second object just through direct contact. Okay, and we'll do things like this in class as an example, but one example could be is if you were to touch an object that could generate electric charge, and then you went and held your friend's hand, they would also get charge as well. Okay, and then they could hold someone else's hand, and then they would get charge, and it would just kind of continue down the line until you could discharge it somewhere. That's conduction, okay, direct contact. Okay, so charges, of course, are always around us, and they are moving all the time. Now, the question we might ask is well, what happens to electric charges once they go somewhere, right? Let's say they build up in my body, and I touch a doorknob, and it discharges. Where does it go? Do they just disappear, right? What happens? Well, there's a law called the law of conservation of charge, and this basically says that electric charges are never created and they're never destroyed. They only move from one place to another. So when objects are discharged, or when charges are discharged or move around, what's happening is a lot of times they'll go from your body to the door, and ultimately they will essentially go into the ground. Okay, so planet Earth is like a giant well of electrons because the Earth is made out of billions and billions and billions of atoms, and all of those atoms, of course, have electrons on them. So the giant, Earth is just like a giant ball of electrons, and so all the electrons that maybe build up on your hand or something that get discharged will want to make their way into the ground so they can connect up with all these other electrons that are there. So the total charge on the whole planet stays the same all the time. It's just that charges are moving all the time. So they might start in the ground and then they get picked up off the ground by, things moving across the ground or maybe up into the air. And then from there, they will, come down from the air to the ground through lightning bolts and other things like that. And just, they're constantly going all over the place, but they never are destroyed or created. They're just kind of going from one place to another. All right, now static discharge, we kind of already talked about this with the static electricity thing, but when you build up enough charge, the charges will want to jump. Excuse me, sorry, it's a bit late. The charges will want to jump from one location to another. We call this a static discharge, okay? Now lightning, and I kind of just talked about this a little bit, but lightning is essentially just a giant buildup of charge in the air that jumps from the air to the ground. A lightning bolt is no different than when you shock your hand on a doorknob. Okay, the only difference is that the amount of charge that is built up in a lightning bolt and going to the ground is a lot larger than your hand to the door. But what's happening is essentially the exact same thing. You have a buildup of charge in one location, and it moves through the air to a second location. Okay, when you shock yourselves, you shock your friends, sometimes you see a spark. That spark is like just a miniature lightning bolt. Okay, but it's the exact same thing as an actual lightning bolt. It's just on a much, much smaller scale. All right, so that is it for this section notes, guys. Hopefully that made some sense. But if you have any questions, as always, make sure that you reach out and ask. Okay, you can email me. We can chat in class. You know, we can always do a Google Meet or do some practice over the computer. But either way, make sure that you get your questions answered. All right, so there will be a video of me going through the practice problems in these notes. And if you want to know how to do those, make sure you go check that out. But otherwise, I will see you in the next one. Bye.